What if I told you that the biggest diamond in the entire universe is not, like, locked away in a vault somewhere here on Earth?
Right, definitely not on Earth.
Yeah, it's actually the frozen, crushed corpse of a dead star, just floating out in deep space.
It's honestly hard to even picture.
I mean, it is a solid, crystalline surface shaped exactly like a planet. And naturally, knowing a giant diamond exists out there makes my human brain immediately wonder, could we send something to land on it? Like, could you actually walk on a dead star?
Oh, that's the ultimate science fiction survival question right there.
Totally.
And the physics required to actually answer it, well, they're going to take us to some very strange places. So to figure this out, we're pulling from two really fascinating sources for this deep dive.
Which are?
We've got stellar dynamics and the physics of celestial bodies, alongside this really great piece called The Physicality of Walking on Dead Stars.
Awesome. Because our mission for you on this deep dive is to completely dismantle what you think you know about the night sky.
Yeah, throw it all out.
Exactly. We want to erase that seemingly simple boundary between planets and stars and really guide you through the universe's most extreme environments.
The places where things just get weird.
Right. Places where the normal rules of matter, the physics you and I rely on every single day to just exist, they completely break down.
And we should assure you, if you're listening to this on a commute or taking a walk, this is not, it's not a dry astrophysics lecture.
No pop quizzes here.
Right. We're looking at the mechanics of the bizarre. But before we can get to, dead stars and diamond crusts, we kind of have to start with the living ones.
Makes sense?
We have to define what a star actually is when it's alive, because doing that completely unravels this massive misconception about the largest planet in our own solar system.
Oh, we are talking about Jupiter. And that super persistent myth that Jupiter is somehow this, like, failed star.
Yes, you hear that everywhere.
I see it all the time. People look at Jupiter, they see it's this massive ball of hydrogen and helium, which are, the exact same ingredients that make up our sun, and they just assume it's a star that didn't quite make the cut.
Like it just missed the mark.
Yeah, like maybe it even has a little bit of a stellar engine running, deep down inside its core.
Well, the sources are unequivocal on this one. Jupiter has absolutely zero fusion or fission occurring anywhere inside of it. None.
Wow. Zero.
Zero. And to understand why that matters, we have to look at the strict mechanical definition of a star. A star is defined by one very specific process, which is nuclear fusion.
Right, which is not just like burning gas in a campfire.
No, not at all.
It's the literal crushing of lighter atoms into heavier ones. You're taking hydrogen atoms, which naturally really want to repel each other, and you're using just immense gravity to force them together so violently that they merge into helium.
Yeah.
And that collision, it releases this staggering amount of light and heat that pushes outward and basically keeps the star from collapsing under its own weight.
That's spot on. And to force those hydrogen atoms to actually overcome their natural repulsion, you need a critical threshold of heat and pressure.
Which Jupiter doesn't have.
Not even close. Specifically, you need temperatures in the core to reach somewhere between 10 and 15 million degrees Celsius.
Okay. And Jupiter's core, just for comparison, sits at roughly 24,000 degrees Celsius.
Right.
Which, I mean, is obviously hot enough to melt any metal we know of here on Earth, but on a cosmic scale, for the purposes of starting a nuclear fusion engine.
It's basically a freezer.
Right. It is hundreds of times too cold to even begin forcing those atoms together.
It's nowhere near the threshold.
Yeah.
The requirement to generate that 15 million degree heat is just pure mass.
You just need more stuff.
Exactly. You need a minimum mass of roughly 0.08 times the mass of our sun to create enough gravitational pressure to ignite fusion.
Okay, wait, what does that look like in terms of Jupiter?
To put that in perspective, you would need to crash about 80 Jupiters together just to reach the absolute minimum starting line for a star.
80. Okay, so the way I picture this in my head is it's like trying to start a massive roaring campfire in the dead of winter.
Okay, I like this.
You can't just use a handful of twigs, right? You need a towering, dense pile of wood to generate enough localized heat for the fire to actually catch and, sustain itself.
Right, it needs fuel.
So Jupiter isn't a failed campfire. Jupiter is just a warm rock sitting 50 feet away from the fire ring.
That analogy actually holds up mechanically perfectly, and it gives us a really simple visual test for the night sky, too.
Oh, really? What's the test?
When you look up and see an object twinkling, you're basically seeing atmospheric distortion playing with the ferocious light generated by a distant star's fusion engine.
Okay. And planets.
Planets emit steady light. They emit no visible light of their own because they have no fusion engine. They're basically acting entirely as giant mirrors, just reflecting the star's light.
Okay, but that does leave a lingering question about my warm rock analogy.
Oh.
Yeah, the sources mention that Jupiter actually radiates about 1.6 times more energy out into space
Right.
than it receives from the sun.
Yes, it does.
So if the core is way too cold for nuclear fusion, where is all that extra heat coming from?
It comes from two entirely non-nuclear mechanisms. The first is the Kelvin-Helmholtz mechanism.
What?
The Kelvin-Helmholtz mechanism. It's basically a process of slow gravitational contraction. Jupiter is massive, and its gravity is constantly pulling all of that atmospheric gas inward.
Okay, so it's shrinking.
Exactly. As the gas is compressed tighter and tighter over millions of years, the molecules rub against each other. That friction from the planet literally shrinking is what generates heat.
Oh, wow. And the second process?
The second process the sources detail is fractional differentiation, which I know sounds super complex.
Yeah, a bit of a mouthful.
But it really just describes heavy things sinking. Deep inside Jupiter, heavier elements and denser materials are very slowly falling toward the center of the planet.
So as they sink through the lighter gases, they're releasing gravitational potential energy.
Exactly. Think of dropping a heavy stone into a deep vat of mud. The friction of that stone pushing its way down generates a tiny bit of heat.
And you just multiply that by billions of tons of material sinking over billions of years.
Precisely. Both of those processes create a massive amount of thermal energy. But crucially, it's just leftover heat from the planet's formation mixed with the ongoing friction of gravity.
So it's a completely different mechanism than stellar fusion,
Completely different.
which really makes the label failed star feel incredibly unfair to Jupiter. You know,
Yeah, it got a bad rap.
if it needs 80 times its current mass just to ignite, it didn't fail at being a star. It succeeded brilliantly at being exactly what it is, a gas giant planet.
And astronomy actually has a specific classification for true intermediate objects, the actual failed stars.
Oh, but they do.
Yeah, they're known as brown dwarfs. A brown dwarf has enough mass to create the pressure needed to briefly fuse a heavy isotope of hydrogen called deuterium.
Which I'm guessing requires a lot less heat than normal hydrogen.
Much less. It sparks, but it just doesn't have the mass to sustain normal hydrogen fusion over a lifespan of billions of years.
But even then, Jupiter's nowhere close to that, right?
Right. Jupiter would need to be 13 times more massive just to reach that incredibly low brown dwarf threshold.
Wow. Okay, so we have a very clear picture of what a living star is. It's a massive fusing ball of superheated plasma.
Yeah.
And plasma means no solid surfaces. Like if I tried to stand on our sun, I wouldn't hit the ground. I'd just fall seamlessly into a cloud of glowing, roaring fog.
You're just vaporized, yeah.
Right. But stars eventually run out of fuel, the hydrogen is depleted, the outward pressure of the fusion campfire stops, and gravity just takes complete control.
And this is the moment the sources dive into stellar corpses.
Yes. And the physics here immediately shift from just, observable space stuff to the completely terrifying.
Terrifying is the right word. The death of a star creates physical states of matter that simply cannot exist in normal space.
Give me an example. What happens to a star like our sun?
Well, let's look at it. When a star roughly the size of our sun exhausts its fuel, it eventually sheds its outer atmospheric layers into space, and the core collapses.
Oh, okay.
So a star the size of the sun gets compressed down into a sphere roughly the size of the Earth.
Wait, the mass stays the exact same.
Yes, the mass stays the same, but the volume is reduced to a fraction of a fraction.
That's insane. You're basically packing a star into the trunk of a planetary car.
That's exactly it. And because that core is no longer generating new heat through fusion, the outer layers of this crushed remnant, which is now called a white dwarf, by the way, begin to cool over millions of years.
And this is where the diamond comes in, right?
Yes.
Yeah.
Under that immense gravitational pressure, the cooling carbon and oxygen atoms actually freeze into a solid lattice.
A physical solid crust. And since it's made entirely of crystallized carbon and oxygen, that crust is, for all intents and purposes, a diamond.
The largest known diamond in the universe is likely the frozen surface of a cool white dwarf.
See, but this is where my brain starts struggling with the mechanics of it all.
How so?
Well, if I have an object only the size of the Earth, but it still possesses the gravitational pull of the entire sun, the downward force must be incomprehensible.
Oh, it is.
So wouldn't a solid crust just instantly buckle, like shatter, and sink straight into the center? How does anything remain solid under that much weight?
That's a great question. Under normal circumstances, with normal atomic matter, it absolutely would collapse.
Right, because atoms are mostly empty space.
Exactly. A tiny nucleus surrounded by a vast cloud of electrons. But a white dwarf is no longer made of normal matter. Beneath that diamond crust is a bizarre fluid known as degenerate matter.
Degenerate matter.
Yeah,
Okay.
gravity has become so overwhelmingly powerful that it has literally crushed all the empty space out of the atoms. The electrons are shoved violently together.
Wait, so the atoms are literally overlapping.
They're forced into the exact same quantum states. And this is where the laws of quantum mechanics step in to basically save the star from collapsing into a black hole.
Oh, wow. How does that work?
There's a fundamental rule called the Pauli exclusion principle, and it dictates that electrons absolutely refuse to occupy the same quantum state simultaneously.
So they push back.
Yes. That quantum refusal creates a profound outward force known as electron degeneracy pressure. It pushes back against the gravity.
So that specific quantum resistance is the only thing holding the star up.
Exactly. And
Right.
it is what allows the diamond crust floating on top of it to remain genuinely physically solid.
That is mind-blowing. And according to the sources, that's just what happens to an average star.
Just an average one, yeah.
If you start with a much more massive star, the death throes are even more violent. It goes supernova, and the remnant it leaves behind makes a white dwarf look quaint.
Oh, a neutron star.
Right.
The pressures involved in creating a neutron star are so extreme that they overcome even that quantum electron resistance we just talked about.
Wait, really? It beats the quantum mechanics.
It does. The electrons are literally crushed into the protons, merging to form neutrons.
Which creates a crust made of an atomic nuclei lattice, primarily iron and krypton. And the sources point out this lattice is 10 billion times stronger than steel.
10 billion.
10 billion. It is the hardest, most rigid material known to physics.
And the gravity of a neutron star is roughly 2 billion times stronger than Earth's.
So it pulls so hard on this ultra-rigid iron crust that as the star's immense magnetic field shift, the crust eventually reaches a breaking point and actually cracks.
Yeah, we call them starquakes.
Starquakes.
And when that lattice snaps, the energy released shoots bursts of high-energy X-rays all the way across the galaxy.
Just incredible.
And just to complete the spectrum of stellar corpses, if a star is massive enough, even the neutron pressure fails.
Gravity just wins completely.
Gravity wins, collapsing the core into a black hole, which has no crust or solid surface whatsoever, just an event horizon.
Okay, so knowing that these solid surfaces exist out there in the dark naturally brings us to that science fiction question we promised to answer earlier.
A walking question.
Yes. We know what the diamond crust of a white dwarf and the iron lattice of a neutron star look like structurally. But what is the visceral, physical reality of interacting with them? Like, could anything walk on a dead star?
Well, the physics of the environment clinically dismantle any concept of walking.
Okay, let's take the white dwarf first.
Sure. The gravity on the surface of a white dwarf is anywhere from 100,000 to 1 million times the gravity we experience here on Earth.
So if you're listening to this right now and you weigh, say, 70 kilograms, about 150 pounds standing on a white dwarf, you would weigh roughly 70,000 metric tons.
Yeah. You would weigh as much as a modern skyscraper, balancing all of that weight on the surface area of 2 human feet.
Okay, so flesh and bone are immediately off the table.
Instantly.
Before your brain could even register the sensation of touching the surface, your bones would basically shatter into dust.
Oh, absolutely. And the immense gravity would instantly compress that organic dust into a microscopic, superheated atomic layer just plastered against the diamond crust.
Yikes. Okay, but let's build a thought experiment.
I love a thought experiment.
Let's engineer a solution. We build a highly advanced robot. No organic parts. We forge it out of solid tungsten and lab-grown diamond, the absolute hardest, most heat-resistant materials we possess.
Okay, go on.
We give it heavily shielded joints. If we carefully, very carefully, lower this tungsten diamond robot onto the surface of a white dwarf, could it take a step?
It's a brilliant concept, but we have to look closely at the mechanical definition of walking.
It is.
Walking is a controlled sequence of lifting and falling. To take a step, your robot has to lift a mechanical leg against gravity that is up to 1 million times stronger than Earth's.
It has to generate upward torque.
Precisely. The amount of torque required to lift a limb against 1 million Gs would demand an internal power source and structural integrity that simply defy material science.
So the motors would just fail.
Worse. The moment the internal motors tried to lift the leg, the mechanical stress would instantly shear the robot's joints and snap its own internal structure.
Oh, wow. So the robot wouldn't shatter from the planet's gravity?
No, it would destroy itself trying to move against it. Unless you possess completely impossible anti-gravity technology, Lifting is impossible. Therefore, walking is impossible.
You would just be immovably pinned to the diamond crust.
Exactly. Pinned forever.
Okay, so the white dwarf pins our ultimate robot. But what if we drop that same solid tungsten robot onto the surface of a neutron star?
Well, the gravity there isn't a million times Earth's.
Right.
It's 100 billion to 1 trillion times Earth's.
Good grief.
Yeah, so the neutron star introduces a completely different mechanism of destruction. Your robot never even makes it to the surface intact due to a phenomenon known as spaghettification.
Wait, really? I always hear that term associated with black holes, but it applies here too.
It applies anywhere. The gravitational gradient is intensely steep. You see, gravity weakens with distance.
Right.
Because a neutron star is so unimaginably dense and compact, the distance of just 2 meters, the height of your robot, makes a catastrophic difference.
Oh, I see where this is going.
Yeah. As the robot falls feet first toward the star, the gravitational pull in the bottom of its foot is exponentially stronger than the pull on the top of its head.
So the foot is being pulled down so much faster than the head that it just stretches the object.
That difference in pull is the tidal force. And on a neutron star, that tidal force is so violently extreme that it would stretch the solid tungsten robot into a thin stream of individual atoms long before it ever packed the crust.
So the structural bonds of the metal are literally ripped apart by gravity alone.
Yes.
A stream of atoms raining down. And what happens when that atomic stream finally impacts the iron lattice?
It splashes.
It splashes.
Yeah, the kinetic energy of atoms hitting a surface under a trillion Gs is so high that the normal matter of your robot instantly splashes as high-energy plasma.
That is wild.
It merges with the surface immediately. Normal matter cannot maintain its structure in that environment. It's instantly crushed into a layer exactly 1 atom thick and just becomes part of the star's crust.
So the very concept of a separate interacting object ceases to exist. You know, this boundary between what is a star and what is a planet starts to feel incredibly blurry when we look at the broader characteristics of these objects.
The lines definitely blur.
For instance, the sources point out that a white dwarf, despite being the crushed core of a star, can actually possess an atmosphere.
Oh, they frequently do. You'll find white dwarfs surrounded by pure atmospheres of either hydrogen or helium.
See, so if I position myself as an alien astronomer flying a survey ship through deep space, and my sensors detect a cold, dark sphere.
Okay.
It's roughly the size of the Earth. It has a solid, crystallized crust, and it is wrapped in an atmosphere. Why wouldn't my alien computer just categorize that as an exotic, heavy planet?
It's a fair question.
Like we spent all this time saying stars are plasma and planets have crusts. Why are we so attached to calling this a dead star instead of just a new kind of planet?
Well, your alien astronomer's visual checklist certainly aligns with the planet. Solid crust, check. Atmosphere, check. Earth-sized, check. But if you investigate how that atmosphere physically behaves, the planetary illusion completely falls apart. The gravity alters the chemistry.
Because of the gravitational sorting we talked about.
Yes, exactly. On Earth, our atmosphere is a swirling mix of nitrogen, oxygen, and other trace gases constantly blending together.
Yeah, it's very chaotic.
But on a white dwarf, the immense gravity instantly drags any heavier elements straight down to the surface. There's absolutely no mixing.
So you're left with what, a hyperpure layer?
A hyperpure layer of the lightest gas, usually hydrogen, just floating on top.
Yeah.
And that gravity is pulling down so hard on the gas that the entire atmosphere might only be a few meters thick.
A few meters. An atmosphere you could comfortably stand up in if you weren't being crushed into atomic dust.
A human height atmosphere, yeah.
Yeah.
But at the bottom of those few meters, resting right against the diamond crust, the gas is compressed so densely by the gravity above it that it actually reaches the density of liquid water.
That is bizarre.
And there are no weather patterns. No high and low pressure systems generating wind. No clouds. It is just a stagnant, ultra-dense, liquid-like skin of gas shrink wrapped around the star.
Okay, so the behavioral mechanics are completely alien compared to a planet. But the sources suggest the true dividing line, the real reason astronomers refuse to categorize these as planets, comes down to origin and composition.
It's all about the history of the matter itself.
Right.
A planet forms from a protoplanetary disk. It coalesces from the swirling clouds of normal matter, dust, gas, rocks that orbit around a living star.
Whereas a white dwarf.
Formed from a collapsing stellar core, it lived a life fusing hydrogen for billions of years before dying.
And the composition reflects that history. Planets are made of normal atomic matter. The empty space inside the atoms is still there.
Yes.
But dead stars are made of that degenerate matter we explored earlier. The empty space has been completely crushed out.
And the density disparity is almost comical at that point.
Yeah, the sources use this classic analogy. If you carved out a piece of a white dwarf the size of a standard sugar cube and brought it back to Earth, that single sugar cube would weigh roughly a ton.
So your alien astronomer wouldn't be fooled for long.
Definitely not.
The moment they measured the mass and radius of that dark sphere, they'd calculate a density 1,000,000 times greater than water. They'd immediately know they were not looking at a rocky planet formed from dust, but the crushed, degenerate heart of a dead star.
It just perfectly illustrates how the categories we use in astronomy are human-made boxes based on the history of an object, not just a visual snapshot of what it looks like today.
We love our boxes.
We really do. But the universe clearly does not care about our binary need for things to be either a planet or a star, solid or gas. It operates on this continuous spectrum of extremes.
The universe loves to blur the lines we try to draw.
It really does. Which brings us entirely back to you listening to this right now. The categories and concepts you rely on every single day to navigate your life ideas like solid ground, weather, or just the simple mechanical act of walking, they're entirely conditional.
They're local rules.
Exactly. They only work here in this specific environment. When the universe is pushed to its gravitational and thermal limits, those concepts completely disintegrate. What we consider to be our fundamental reality is really just a very, very narrow band of normal physics.
We essentially exist in a highly localized illusion of stability.
We really do. And to leave you with one final kind of mind-bending implication to mull over today.
Oh, lay it on them.
We talked about how the gravity on a neutron star is 1,000,000,000,000 times stronger than Earth's, right? Stretching metal robots into atoms.
Spaghettification, yep.
But general relativity tells us that extreme gravity doesn't just pull on matter. Extreme gravity literally warps the fabric of space and time.
Ah, yes. The stronger the gravity, the more it slows time down.
Right. The time dilation at the surface of a neutron star would be just staggering.
Completely warping your perception.
So imagine for a brief second that our tungsten robot experiment worked. Imagine you possessed some impossible magical technology that allowed you to actually stand on the iron lattice of a neutron star, perfectly surviving 1,000,000,000,000 Gs of force.
Okay, I'm imagining it.
As you stand there, plastered to the crust, time for you stretches out, while you experience what feels like just 1 minute ticking by on your watch. How many millennia are passing by in the cold, dark, normal space above your head?
A lot.
Yeah. If you ever managed to step off that star, you would be stepping out into a universe that has aged thousands of years without you. Just something to think about the next time you look up at the night sky, trying to spot those steady, quiet points of light.